Everybody just candidates, it's just like, see every.
That works, right?
Yes.
We're usually waiting 1 more minute for the next people to come, and then we can start. Okay, so welcome everyone to the New Technologies in Mathematics seminar. Today we have the pleasure to have Anirudh Goyal, who is a research scientist at DeepMind Google. And so we'll be talking about how to go from word prediction to complex skills and some principles about foundation models. So take it away.
Hello, everyone. Thanks for taking time. I'm Anirudh. I'm going to talk about some of our work which we have been doing. It's a collaboration with lots of PhD students, actually advised by Sanjeev Arora and Yasha Benchio. Feel free to stop me at any time during the talk if there are any questions. Very happy to entertain them. Okay. So if we think about it, like the perspective on machine learning has kind of moved. A particular old view was given a data set, train versus test. We try to model the training distribution as well as possible, such that the accuracy on the test set is high. The emerging view is basically our users kind of demand a competent model, and as of now, we'll do whatever we can to deliver it. So that means whether they're changing data distribution, whether changing evaluation metrics, whether employing new algorithmic techniques. And because of all these secrecy, people have even started publishing less and less about what kind of ideas and what kind of algorithms are people using. And doing this correctly has kind of become the black magic of real AI systems. So just to provide a quick high-level overview, the basic idea is you try to take all the possible data which you can think of, you try to convert that data, and you feed that data to a particular language model, which tries to predict the next token. So imagine you have a particular piece of text, and you know what the next token should be. You ask the language model to output a probability distribution or all the possible vocabulary, which in LLM term called tokens, and you penalize the model in order to update the model such that it is able to accurately predict what the next token should be. And the best language model is the one that basically best predicts an unseen test set. So whichever the one which gets the best test set. What made this kind of LLMs popular is basically as you scale up these models in terms of data as well as in terms of compute requirement, the performance keeps on improving. As well as we have seen that certain capabilities emerge at larger scale. Scale means either in terms of compute or in terms of data, which were not present in the smaller models or the models which were using less compute. So at a high level, what you're doing is basically you take lots of diverse data set, you feed that data set to a particular neural network, you train that neural network by next token prediction, and certain skills emerge. It could be language skills, it could be coding skills, it could be logical skills. The interesting thing to note here is in the loss function, there's no incentive or there's no inductive bias on the model to actually acquire these skills. As a result of next token prediction objective, the only way for the model to figure out how to develop the underlying structure, how to learn the underlying structure of this diverse data set is to end up learning these particular piece of skills. So as of now, we don't have a particular idea or particular theory as to how we can explain like why these skills emerge as models are scaled up. We don't have a theory for neural networks in general, even though we have made lots of progress. Now, this question is particularly interesting, relevant even for safety, because we don't know what kind of skills would emerge if we train the model for much longer as well as much bigger. The second thing which is interesting is, can we actually change the incentive structure? For example, as of now, the incentive structure is next token prediction. Can we change it to a better loss formulation, a better loss function, which can accelerate the learning of these language skills or other skills? So just to give an idea kind of tailored towards mathematical reasoning, imagine a particular problem. The points A and B are adjacent vertices of a square, and you ask the model, what is the area of the square? Now, in order to ask the basic question, you basically need like three particular skills. Basic reading comprehension, which can tell you how to make sense of this particular question, how to compute the distance formula, as well as how to compute the area. Now, once you have learned these particular three skills, you can basically answer lots of these questions, which involves random unseen combination of these three basic skills. An interesting debate which has been happening in our field, whether these language models are basically stochastic parrots in the sense that they are basically can only predict things which are known in the training distribution, or they actually understand something. Partly because we still don't know what is being fed to train these models. It's always a mystery as to whether they're actually understanding something or whether something is actually the part of the training distribution. So how can we actually go about kind of solving this dichotomy? In order to actually understand this, let's try to think about how we actually train these models. So what happens is at one of these places, whether it's DeepMind, whether it's Meta, whether it's OpenAI, etc., we have a collection of tasks. And collection of tasks here basically means next token prediction on web curated data. We train the model to solve these tasks. By solving these tasks means literally next token prediction. Once we have trained the model, during the training process, we evaluate the model on different skills. It could be like how good the model is debugging code, how good the model is in editing code, how good the model is in problem solving, how good the model is in other skills. And we try to identify the ones that needs improvement. And based upon this, we try to gather data, whether it's targeted data, whether it's synthetic data, whether it's curated data, whether it's licensed data, in order to update a collection of tasks. So it's basically a continuous cycle of task generation, training, and evaluation to enhance the model skills. The two processes are useful. One is learning to solve known problems, which basically involves that you have lots of tasks, you train the model to solve this task, and you evaluate the model on specific skills. The interesting thing gathers into how we actually get the data in order to generate new tasks, such that you can teach the model new skills, or you incentivize the model to learn the new skills. That process basically involves you evaluate your model on different skills. As I said again, the skills here means how good the model is in debugging code, how good the model is in theory of mind, how good the model is in language skills, etc. And then you basically collect data such that training on that particular test set, or training on that particular data distribution would teach the model how to develop specific skills. And the cycle kind of goes on. Now, the interesting question is, how can we bootstrap this process? How can we basically teach the model, or how can we know which data distribution the model should be trained on, as well as how we can generate tasks in a targeted fashion? Like as we are training these models on lots and lots of data, probably all the data, there's an estimation that in the next few years, we would basically exhaust all the data which we can think of. So it basically requires new, interesting algorithmic ways to figure out what kind of data distribution should we train the model on in order to teach the model or in order to incentivize the model to learn new skills. That raises the basic question, like, do advanced LLMs have actually capabilities that were not present in the training distribution? Now, in order to know that whether those capabilities were not present in the training distribution, we need to know the training data. But of course, we don't have access to the training data. Second thing is the set of all possible capabilities is just too large. So we don't even know how do we test. So the first part of my talk is kind of going to present a framework which deals with this particular question. How can we evaluate these language models in a way which actually tells you how good the language models are in combining different skills? Then I'm going to use that particular insight in the domain of mathematical reasoning to ask the model how to come up with those skills themselves. And then I'm going to talk about how can we use those kind of fine-grained skills such that model can generate new questions with human in the loop, whether it's a training set or whether it's an evaluation set. Okay. So what are the issues in evaluating these LLMs? The first one is data contamination. Since these models are trained on the entire internet, we don't know what's present in training distribution as well as test distribution. Most of the common evals which we have been used have basically very high contamination rate with the training distribution. So what happens is the examples similar to the ones on the evaluation, they end up in the training distribution. And it's really hard for us to actually even figure out what kind of data went in the training and evaluation because the verification itself is very difficult. Like doing exact substring matching with respect to entire training corpus is actually a difficult process, which actually also doesn't catch up. Like, what if you have a particular problem and someone converted that problem into multilingual and that went into your training distribution? Exact string matching or exact verification won't be able to figure out certain scenarios where there's actually contamination, but we don't know. The other point is about model originality. If we don't have access to the training distribution, we don't know whether the model is actually creating something new, or is actually creative, or is actually just spitting out your training distribution. And this debate has been happening in our field under stochastic parrots versus understanding. The third issue which is prevalent is the access to these leaderboards. Right now in our field, we have these leaderboards, whether it's Hugging Face, whether it's other ones, and we want our models to be on top of that. But in order to be on top of that, what sometimes ends up happening is we kind of deliberately train on data similar to the leaderboard evaluation tasks. And we have seen that the top models on the OpenLLM leaderboard sometimes performs worse when you actually chat with them. So what's the desiderator for basically next generation evals? It should be relevant to the general purpose intelligence as well as language understanding. These should be easy to design and evaluate. Like if coming up with an eval requires an expertise of a PhD, it would be really hard to scale it up. The particular eval should be resistant to data contamination, so we shouldn't know whether that data is within training distribution or not. We should be able to figure out what's the capability of revealing the novelty. So if the model is able to answer new questions or new problems, we should be able to figure it out whether it's going beyond the stochastic parrots, as well as it should be resistant to cramming for leaderboard. And the last thing is we should have a knob which could basically which is basically adjust the difficulty level, like how difficult questions which we can create. There's a spectrum, like if they're too easy questions, most of the models would be able to answer. If it's too hard, then none of the models would be able to answer. So we need to be able to adjust the difficulty level so that we can actually know whether we are making progress or not. We came up with this idea which we call skill mix evaluation. The basic premise starts with, like, all these language models are trained on Wikipedia, so they exactly know what different language skills are. So we start with a set of n language skills, example metaphor. So these are the skills which linguists have basically said that a particular person should possess in order to know whether it knows vocabulary. Then we start with a list of T topics. These topics can be esoteric. Esoteric in the sense that not necessarily the model knows about it or heard about it, but it's in the training distribution somewhere. And what we do is we randomly pick a subset of K skills. So K could be 1, 2, 3, 4, 5, as well as the random topic. And we ask the model to output a short piece of text in the context of topic and illustrate all the K skills. So what we do is we pick a set of N skills, we pick a set of T topics, and we ask the language model to output a short piece of text which combines all those skills and all those topics. So visually, we call it skill mix ecosystem. We start with a list of N skills. N could be hundreds. We start with a list of T topics. T could be 100. We pick K skills, and we ask the model to whether the model generated text actually shows all those different skills as well as on the topic. Now, first, this particular evaluation is fair for all models of all sizes. And the second thing is it's very easy to expand skills as well as topics. So there's no way like someone can actually cram for it. Other thing is you can actually make the problems a lot more complicated by increasing the number of skills it's required to actually come up with an answer. So if you increase the K, the complexity of the prompt actually increases, but the complexity of the task actually increases. So let's say we start with N skills, T topics. We ask the model to combine K skills. These are the possible combinations for large enough N or large enough K. We can actually show that it's not possible to see all these possible combinations in your training data. And basically simple probability calculation shows that random topic as well as set of 5 skills are basically very, very unlikely to have occurred in the training corpus. And as of now, the best frontier models actually succeeds often for K is equal to 5. But again, as you increase the K, and the performance of all the models decreases. So the main result is we try to attempt to evaluate the general purpose language capabilities, which in these terms called compositional generalization. We evaluate the model as to how easy is it for the model to combine different skills in the context of different topics. We saw that the performance of models on skill mix generally accord with the popular perception. So GPT generally performs the best as compared to all the other models. We are also able to figure out signs of cramming of the leaderboard. So some of the models which are actually on the top of the open source leaderboard, they actually perform much worse on our benchmarks, on our eval. And based upon it, it also shows that some of these models actually passes the stochastic Parrott's view because the probability of seeing 5 skills and random esoteric topics is actually very, very less under the training distribution. So there's no way they're actually just doing string matching to output something from a training distribution. Up till now, I've talked about that we can think about language models as inducing skills. And we can evaluate these language models on the abilities of combining these different skills. Here I'm going to talk about taking the mathematical problem solving as an example, do language models actually know what skills they are using in order to solve a problem? So imagine I gave a particular question. A container starts with some water. Each minute, the scientist adds some amount of water. What's the smallest integer? That the number of liters of water is never in the interval, something. When you're actually thinking about the problem, you know what you're thinking about. You know what are the strategies you need to use in order to solve the problem. And this particular idea is called metacognition, where the humans are reasoning about their own thought process as to what's going about when they're actually thinking. And psychologists have studied a lot about this particular problem, as well as in pedagogy, as to what are the good ways of humans for developing problem-solving skills, and what kind of behavior is being employed by the humans in order to solve that. Coming up with these questions, I told you that, or we discussed that, in order to solve this question, we require these skills. But these skills are enforced by the humans. Now we ask the particular question, do actually language model themselves know which skills are required in order to solve this particular question? Because if that's the case, we can actually kind of interpret what kind of strategies these models are using in order to solve these problems. So we thought how to go about exploring this problem, and it was not obvious. And the simple thing we started with is, given a mathematical question, can we just ask LLM for the skill it would require to use the question? It was not obvious what the results were going to be, but one reason for doing this particular experiment was like all these particular models have seen the data which is present on the map on the internet. So they know what different skills are because that's present in our textbooks. And we just wanted to see, given a novel problem or a new problem, can the language models or can these models know what skills it would take in order to solve these problems? So what we do is, given a mathematical problem, we prompt the model, can you figure us out what skills you would require in order to solve this particular question? As well as give the rationale as to what are the particular reason of using those skills to solve that problem. So the first step is, given a mathematical question, we ask LLM for the skill it would use to solve the question. So imagine we have a catalog of skills, a catalog of questions. We ask a particular language model, let's call that LLM-A, and it assigns kind of a fine-grained skills, skill 1, skill 2, skill 3, skill 4, skill 5, to all the different questions which we have in our training set. It could be, just to give an example, a very popular mathematical problem dataset called math or Hendrix math has around 5,500 questions in the test set. So imagine running this process over 5,500 questions. Now the problem is these particular skills which are being employed by the language model would be too fine-grained. So what we ask again is, we ask the GPT-4 or ask the frontier model, can it partition the large number of latent skills into clusters? So we have particular fine-grained skills. We ask the language model, can it basically cluster them to have some sort of course level skills? The interesting thing to note here is it's basically clustering, but there's no vectors involved. There's no geometry involved. There's no distance formula involved. We basically feed everything to the language model, and we ask the language model, how would you cluster it? Once we have these clusters, we basically ask the language model to relabel all the questions to be in one of those clustered skills. So imagine after the step 2, we clustered all the questions into 3 skills, and then we basically make a bipartite table where we know that what those skills are and which question actually uses those skills in order to solve it. Now, once we have constructed this particular repository where the keys are the skills and the values are which question uses those skills, how can we use that? The one particular thing is when you're trying to solve the problems, we try to even find what axiom to use or what kind of examples to use. So we can dynamically use these examples in the repository to form the basis or to provide context for the language model to solve unseen problems or unseen questions. So we have examplers where the keys are skills as well as values are what questions requires those skills. Given a novel problem or given the new problem, we basically select examples which are relevant for that particular problem based upon the skill. So what happens is, given a particular test question, we ask the same language model LLM-A to output a particular skill which is required to solve that particular test question. Now, using this repository, we take the examples which is relevant to skill 2, basically question 2 and question 5, as in context information, and we provide that information as in context to the language model, to another LLM, such that it can use that information as in context to solve different problems. So the complete pipeline is something like this. The first one involves creating the skill example repository, where in the first phase, we do skill labeling. Given a set of questions, we ask the language model to assign a particular skill. These skills are too fine-grained, so we do some clustering. The second phase is also called skill clustering. Here also no k-means clustering is used. We use basically the language model itself as a way to figure out how to cluster these fine-grained skills. And a result of the skill clustering, we have basically a repository, which basically knows that what skills are, where the keys are basically the skills, and the values are what mathematical problem it requires to solve those skills. And during test time or inference time, given a test question, you basically ask the language model to figure what skill is required to answer that question. And based upon that skill, we select the relevant information from the repository, and we use that information as in context to compute the final answer. The one thing which was interesting to note here is we basically found that the LLM-A, which creates the skill repository or skill exemplar repository, as well as which uses this in order to compute the final answer, they may not be the same. So the skills which are constructed via a more powerful model actually can help bootstrap or improve the performance of a weaker model. So in this case, LLM-A is a stronger model and LLM-B is a weaker model. We also try to analyze whether this particular clustered skills are actually doing some correlation or actually some meaningful information is being transferred. So we try to apply the similar idea for code generation, where instead of asking the model to solve the particular problem in using just pure text, we ask the model to write a piece of code. Because if the model knows how to write a piece of code, the text information can basically help bootstrap the understanding of the model. So we ask the model to generate code, but we provide the skill-based information as in context in order to generate code from the LLMs. The normal strategy which people use is they provide different examples as, it should be example 3, as in context examples, and you have a new question and you ask the model to output a piece of code for that question. We basically use the text-based in context examples from previously to improve the code generation. So we replace, let's say if we are using 3 code examples, we replace 2 of them with actually skill-based examples which have no code whatsoever. So this basically involves just pure reasoning, but it tells the model that if you want to write a piece of code in order to solve, in order to compute the area, you first need to compute the distance formula, and then based upon the distance formula, you need to write something area. So across different models, providing text-based in-context examples can actually improve the performance by around 7% on absolute scale. We have tried on various different categories. So whether it's interalgebra, whether it's pre-calculus, whether it's geometry, whether it's number theory, probability, algebra. So on an average, using the text-based examples actually improves the performance 7% in absolute terms, as well as 10% when you actually increase the number of examples which you are providing to the model as in context. One thing is the particular phenomena is not just limited to the math problems. You can actually apply the same strategy to all the other domains, whether it's business strategy, whether it's creative writing, whether it's biology, whether it's fashion, whether it's ethics, etc. Okay, so in the first part of the talk, I talked about that we should think about these language models as inducing skills and how we can use those intuition of skills in order to ask the language model to combine skills to generate data which can allow the model to evaluate its generalization abilities. In the second part of the talk, we asked the question how good or how bad the models are in order to coming up with these skills themselves. In the third part, I'm going to basically use information from the second one to basically see, can we bootstrap the process of evaluating language models on more and more difficult questions, but where the questions generated are generated by the language model itself. As of now, the mathematical reasoning is basically positioned as one of the core capabilities of intelligence, it's been the case across all different frontier language models, whether it's Claude, OpenAI, Gemini, or Llama. Now, the same challenges lies here for mathematical LLM evaluation. Whatever the available sources of high quality data are drying up. New benchmarks generally include very, very difficult exams, which requires like mathematics PhDs. And in order to come up with these, different companies are spending millions of dollars to actually create data which is used for both training as well as evaluation. So how can we address these challenges? And by challenges, I meant how can we ask the model to come up with these questions itself, such that using those generated questions and getting feedback from the humans, it can create a training data itself. So some sort of a bootstrapping pipeline. Now, if we come up with new evals, they need to be sufficiently out of distribution with respect to standard training and evaluation benchmarks. And one thing which we can use is, in the first part of the talk, I talked about how using more and more complex skills, it basically improves the complexity of the generated prompt. So how can we use that insight to create out of distribution examples with respect to both training as well as evals? And another important thing is, how can we come up with a scalable approach to generate such data sets? So how can we address this challenge? The basic answer lies in the one which I just talked about, looking at questions as composition of skills. And noting the insight that as you increase the number of skills needed to solve per question, the difficulty of the question also increases. So what we do is we use a popular math dataset. It's actually just called math. we run the skill extraction pipeline from the previous part of the talk in order to come up with a skill example repository where we know what are the different mathematical skills are and what are the problems to come up with those skills. Once we have that skill category, we come up with a multi-turn prompting pipeline, which basically uses these language models themselves in order to come up with these harder and harder questions. So the first step is we ask the frontier language models to assess the similarity of sample skills. So we give them a particular set of skills as well as question and solution which involves those skills. That particular part is given as input to the frontier language models. If you're asking the language model to generate questions, let's say which combine two skills, we first ask the language model, are those two skills distinct enough to be combined in a question or not? If the language model says they are too similar, we actually stop the process and start repeating the process again. If they actually say not too similar, we basically continue to the next step. Now, given those two skills, we ask the frontier language models to generate a new question. So from the step one, we ask the model, please generate a question which combines the application of two given skills. And the language model, after doing some internal thinking, it comes up with a particular question which combines or tests the application of those two skills. Now, the thing is, we don't know whether the generated question actually combines the application of those two skills or not. So in order to address this scenario, we again ask the frontier LLMs to attempt a basic solution. So given the generated problem and the skill example repository, we ask the LLMs, try solving this question and try to see whether there's any ambiguity or whether you can actually solve the problem itself or not. And model tries to attempt a particular solution. So if the model says that it's able to attempt a solution, whether we know whether it's correct or not, we assume that the problem is solvable. And the next thing we do is we ask the frontier LLMs to actually verify the question, whether the verified question actually makes sense or not. We come up with several criteria to basically test whether the generated question is verifiable or not. We make sure that the particular generated question has a single answer. We make sure that whether the generated question have an exact answer or not. We also make sure that the generated question requires a rigorous skill combination. We also make sure whether that particular problem is actually realistic and involves logic. And sometimes the model just generate questions which are junk, and based upon certain filters, we basically filter out some questions which doesn't make sense and the questions which are invalid. And now the last step is when the model has been through all these different processes, we ask the language models to basically provide a final solution. Can you please verify this particular question thoroughly and accurately? So at a high level, it basically involves a 5-step process. The first one, whether the combination of skill pairs makes sense or not. We call this process skill pair validation. The second one, given those verified pairs, we ask the model to generate questions. The third one, once the question has been generated, we try the model to attempt to solve the particular problem. And the fourth one, once we know that the model has the question generated as well as the answer, whether the question and answer are consistent with each other. And the fifth one, if we know that the question makes sense, how we know whether the final solution is correct or not. Now, the one interesting thing is when the model is able to generate the questions, we still need to know what the final answer is. And this is where humans comes into the picture. Because when generating these particular questions, these models makes lots of mistakes. Sometimes in the particular generated question, the information is incomplete. It doesn't tell you what the human should actually do. Sometimes the given skills, they are not sufficient involvement of both skills. Sometimes there's extra information in the generated question. So the model itself tells you how to solve the problem. Sometimes it generates question to which there's no feasible answer. So computationally intractable questions. And sometimes the generated questions are basically nonsense. So the last step of the process, humans verify the questions and increase the difficulty, improve clarity, and correct the solutions, etc. So we applied this pipeline on a very popular math dataset. We call the resulting dataset math square. These are 210 generated questions which are generated by the model itself, and the humans have verified it. We try to generate different questions from different number of models. So GPT-4, Gemini, Claude, etc. These are the basic statistics. So out of the 200 examples or 210 examples in our generated datasets, the humans had to modify 64 questions. The humans have to modify 136 problems. And the combination or the union of modified questions and modified solutions, whether one of, like in those scenarios, whether the human has to verify the question or the solution is 139, and the total dataset size came to be around 210 questions. Now, one big difference from the original dataset math is basically the generated dataset only uses those skills which are all present in the math. The only thing which is changed is in the generated dataset, instead of just testing a single skill, it tests the ability of the model to generalize in a compositional way, that the model should be able to apply multiple skills to solve the problem. Once we have generated this particular question, or 210 questions, we actually compared the performance of all the models or all the prominent models on the original dataset as well as the math square. And we noticed that the performance actually decreases, ranging from 16% to GPT-4 Omni to like 94% to some of the MetaMath datasets with respect to the original math datasets. Now, this result is interesting partly because in the generated new dataset, math square, no new information is being judged. The set of skills which are required to solve math or to solve math square is exactly the same. The only thing which is different is some of the math problems only require single skills, and by construction, some of the math square problems requires combining multiple skills to solve the problem. We also try to find patterns as to if there's a correlation between the performance of models on math as well as the performance of model on math square. And we interestingly found there's a pattern where, in this case, on the x-axis, we have the performance of the math dataset. On the y-axis, we have performance on the math square dataset. And we found that the pattern is basically y is equal to x squared. So whatever the performance is on the math, and the square root of that is basically the performance on the math square. And all the models which basically are listed here, they all kind of satisfy this particular constraint. Now, one way to intuitively think about it is just by construction, math square requires multiple skills. So if there's an expectation or an expectation, if there's an error E, just because you require multiple skills, it gets doubled. Sorry, not doubled, it gets squared because you're taking into account multiple skills as compared to one. So the simple expression is quotient in math requires 1 skill at a time in order to be solved, whereas quotient in math square requires 2 skills at a time. So the error rates basically gets multiplied, and that's why we see y is equal to x square relation. So just to zoom out, the first part of the talk dealt with how we can think of these language models as inducing skills, and then we came up with the pipeline which tests the ability to combine those skills. The second part of the talk about how can we use the language model themselves in order to bootstrap how to come up with those skills, because like if we ask some humans, it would be really hard to do it at the scale of billions or trillions of tokens. And the third part of the talk talks about how can we use these fine-grained skills to come up with new interesting questions where the questions are generated by the model itself, and there's a human in the loop which tries to provide some feedback as to how to improve the questions or how to improve the solutions. Here I'm going to just talk about very briefly, we have been thinking about, can we come up with a way which can give a theory as to why this emergence happens, like when you're scaling these large language models, when and what skill appears at what time. So this is the work done by Sanjeev Arora, where we come up with basically interested in how can we explain that the new capabilities arise as you're actually scaling up these large language models, and give it a more precise and mathematical definition of what a skill is and what a language corpus is. I'm not going to talk about that theory work in general, but I'm just going to give a high-level overview of the main results of what the result of that work is and how that corroborates from the finding from the experiments. So the basic intuition is from this example, which I mentioned earlier. Imagine there's a particular problem. The points A and B are the adjacent vertices of a square. What's the area of the square? Let's imagine there's an oracle which inserts these closed questions such that in order to answer these closed questions, it needs to combine those multiple skills. So in this case, the skills are basic reading comprehension, compute distance, compute area. We make an assumption that imagine you can insert these closed questions in all the training corpus of the dataset, of models dataset. Imagine there's an oracle which can do that. So whatever the model's average error is in these closed questions is basically excess cross entropy. That is the kind of mistakes the model is making is kind of directly correlated with the model's average error in these closed questions. And what our theory work does is it tries to relate this particular excess cross entropy with the formation of these skills. So we basically show that as these models are scaled up, either with respect to data or with respect to the compute, basically the parameters, the model's ability to come up with these closed questions or to answer these closed questions increases. So it's able to answer them more and more correctly. So the main result are, as we scale up the model's competence on combining the k tuple of skills increases. It also shows that for a fixed prediction loss, it's actually better to use higher k. That is, we should train the language models on those pieces of text which requires more number of skills. It also shows that it also proves that why competence on k-tuple of skills, or why the generalization occurs on the k-tuples of skills that have never seen in the training distribution. The basic conclusion is the ability to compose skills implies some degree of novelty. So if the model is able to combine skills which it has not seen during training distribution, it implies that it's not just doing some string matching, and there's some degree of novelty and some degree of generalization outside of its training distribution. I don't provide a strict definition of what the skills are in this talk, but I note that we can get this human defined or human intuitive knowledge of what the skills are via asking the LLMs itself. And we call this basically LLM metacognition, where the model itself is coming up to know what is required to solve the problem and is reasoning about that process. And the second and the third part of the talk talks about how can we leverage these metacognitive abilities to come up with new LLM evaluations. So here, this would mean that how can we use the skill catalogs to come up with new difficult questions, which we can use as an evaluation set. B, we can also use that data not just as evaluation set, but as training sets. So the model generates the question, humans provide the feedback, and we can use these generate questions as a training set. And the last one is how can we understand, as the models are scaled up, how can we know in advance, like what capability is going to emerge on 10x more compute or 10x more data distribution. Thank you again for taking time. I appreciate it.
I have a question. Can you hear me?
Yeah, I can hear you.
Okay, yeah, I mean, there's a lot there. It's very interesting. Let me just focus on the first steps of your procedure in the middle of the talk of producing a list of skills. Was, if I understood, you have a bunch of, in this case, math problems. You have a set of problems. You ask models to describe skills that could be used in solving these problems. Then you had a refinement where you had GPT work go through and produce clusters and then produce some final list of skills. Was that right?
That's right.
And so that process really is no human intervention. It just takes the list of problems and ultimately produces a list of skills and with your song.
Yeah, that's exactly it. So the input to the model is just list of prompts, and the output is basically the list of skills as well as which prompt shows the application of which skill.
And it's very intriguing. As you say, it's a metacognition. Just one kind of sanity check I'm curious about. If you replace the word skill with other words, how similar is the result? So it list, other synonyms, things that are like, not skill, but who knows what, Did you try that?
Yes, I don't have this in the slides here, but in our paper, one thing which we did is we tried to measure the performance. You can think about this kind of a process as clustering, but the model itself is doing the clustering. So there's no vectors involved. There's no nearest comparisons involved, etc. And what we do is we come up with an explicit clustering baseline where we compute the distance in the space of embeddings, and we use that as basically skill clusters. So basically, we take all the math data set or all the prompts, and we cluster them into k categories, the same categories, and we try to see if the model is able to come up with kind of a similar interpretable categories, and we never got the same result as the proposed method.
Well, just so you weren't able to duplicate the asking the LLM method with any kind of mathematical or embedding-based method, is what you're saying? Or
Yeah, that's right.
Similar, but not as good, or just really nothing?
It improved the performance over the baseline, but it was not the same. there was like 10% relative decrease in performance as compared to LLM using itself.
Okay, that's a related question to my question. I was just kind of ignoring the simple-minded experiment. Instead of saying skill, say law, say ability, or say job. Just I mean, to what extent is the model relying on some kind of corpus, knowledge about skill? To what extent is it doing clustering internally and so forth? Right. I mean, that word skill is it significant? It might be.
So we have been verifying this particular premise along different kind of domains. And what we found is domains which have some logical structure to it, like maths, as well as kind of STEM topics. It is actually a big difference between these skills as kind of logical procedures as compared to just some factual knowledge. But in some other domains like normal language skills, these skills are not just actually logical procedures, but actually just some knowledge, like whether this is, so there's a kind of a difference between knowledge versus skills. And the premise is the more logical structure a particular domain has, the more fundamental the unit would be for skills.
Yeah, I mean, actually, this is another question I was thinking of asking, and you kind of brought me to it, which is that if I just look at the procedure formally and ignore what everything means, it's not that different from like RAG, retrieval, where you had a list of source documents, you have some kind of keywords on them, you supply those as in context, prompts, right? I mean, formally it's very similar, right? Just
That's right.
In your case, it's not knowledge, it's skills.
That's right.
Yeah. Okay.
I have a small question. So coming back to the diagram where we compared math and math squared for like the different models, can you just re-explain if you use like all the 200 questions or only the kind of 33% which were not kind of corrected by humans?
No, for the math score, we actually used all the 210 generated questions, and we didn't use only the ones which are modified by the humans. We also analyzed if a human modification actually makes or actually improves the difficulty of the question, but we didn't found any evidence of it. The model's performance on the original questions as well as the model generated questions, which are verified by the humans, were actually approximately the same.
Oh, I see. So if you like use only the 33% not corrected by humans, it's kind of the same drop in accuracy. It's like kind of the same increase in difficulty. Okay, thank you.
So that was also surprising to us. The one big thing which we found though, like the capability of generating questions is kind of only present in these 4 models as of now. We tried to use some kind of an open source alternatives, and we didn't find any evidence that they're able to generate interesting questions.
Okay, thank you. Any further questions for Anirudh? And on Zoom? Okay, in that case, let's thank our speaker again.
Thank you for taking time.
Thank you very much.